Admit. Good. Okay. All right. Yes, I just joined it. So it should be open. I'm in it right now. And I think Yancheng is also in it, so he can admit people too, I hope. View everyone in this call. Admit one guest. Okay, here we go. There we go. Cool. All right, how's everybody doing? Mostly awake, seemingly. It's still kind of dark in here. Let me see if I can fix that. Aha. Good enough. Okay. So congratulations to Kunal and Runlin. Where are you guys? At least one? Does Runlin or Runlin, or where are you at? You're here. Dang. Okay. Well, we still had a gravitation of people onto like sort of popular papers. Do you want to explain your strategy for picking a unique paper?
Oh, sure. It's the big algorithm I deployed. It's called wait till the last minute. Whatever.
I see. Well, there was a few options on the table actually. This is a nice one. Oh, I think I added this at the last minute. Maybe that's why no one got that one. But yes, okay. Very nice. Thanks, guys. Any questions about the unique paper bonus or reading so far? Concerns, comments? Oh, do fill out the course evaluation. I post about that on Ed. It actually really helps me to make things better. So if you don't feel brave enough to say in class that this thing is a stupid mechanism, you can say it anonymously, which I appreciate actually. All right, cool. So today we're going to be finally getting into multi-agent RL, which is like one of the most fundamental topics of this course. So I'm really excited about that. So why is multi-agent RL harder than regular RL, arguably? What do we think? Yes. There's multiple agents. Yes. And what does that do? Why does that complicate things? Yes.
Like there's no like equilibrium, right? Like if one agent gets better than like the other agent. Something to do with that. I forgot.
Yes, there actually can be an equilibrium, but yes, as one agent gets better, the other agent might also be changing. So kind of the ground is changing underneath you. Nothing's stable, which we'll talk about. Yes. Any other thoughts? Yes.
Coordinate. So there should be like protocols on how they can coordinate.
Yeah, they need to coordinate well. We have to find like a shared strategy space. We have to sort of simultaneously settle on those actions that to coordinate. Yes. If we take it back to LLM land, if we think about interacting with a user, I guess I didn't teach this super explicitly, but we're hopefully familiar with the formalism of a Markov decision process, right? What's a Markov decision process? MDP. You just answered in the back, yeah.
It's like basically a graph like states and like probability states.
But what's the Markov property? Yes. The current state is independent of, like state at time t is independent of state at time t minus 2, etc., given state at time t, right? So state at time t contains everything I need to know about the past. Is that true in a dialogue setting with a user where the state is the conversation you've had with that user so far?
No.
Thank you. No, it's not, right? I don't know everything there is to know about what's going to make the user formulate their next response because that's in their brain. And their entire brain is not contained in the state. So what does that imply about interacting with a human or potentially another agent? Is the Markov property true? Depends what your state is. That's fair. So if I can condition on all of your neurons, maybe if you're a materialist, we think that would be true. But if let's say we can't, right? Then what is the problem? What am I getting at here?
Basically, other agents, states, not usually other states.
Yeah, exactly. So because the intentions, beliefs, goals of the other agent are quite often hidden, almost always hidden, we're typically in a POM DP. The observation is what we can see about the world. So this might be like your dialogue. That's what we condition on. But the true underlying state contains hidden information about like the user or the other agent's policy, beliefs, goals, preferences, etc. That makes sense? Cool. And we'll go into the point Eric brought up too. So in traditional RL, we're doing this Bellman equation, right? So we get the actual observed reward for this action, best estimate for the next Q state, we iterate, and there's actually some guarantees that this will eventually converge to the Q value of the optimal policy. So that's pretty cool. But we often assume that we're given this state transition function, which says what state I can expect to experience if I start in this state and take this action. When we, and this state transition function is a property of the environment, so it describes that probability. It's often written as this T. This gives you some nice theoretical guarantees that RL will converge to the optimal policy as long as you get enough data or enough samples. So these go back to like 1992 for Q learning. There's proofs for policy gradients as well, which you can check out the Sutton and Bartow textbook to learn more about. But these guarantees depend on that state transition function being stationary, meaning every single time that I'm in state at ST and take action A, I get the same transition to ST plus 1. What's the problem? Where am I going with this? Eric actually kind of said it already. What happens in multi-agent setting? Yes.
The other agent might do something.
Exactly. So the other agent is learning. They have a policy. They're going to pick some other action that's not always going to be the same. And so as you're learning, your state transition function is actually non-stationary. Yes. So if you look at multi-agent RL and we write this down a little bit more formally, we can think of other agents as part of the environment, and they actually affect the transition dynamics you experience. So hidden in this equation is some other agents choosing their actions, and that actually affects the probability of seeing a particular next state. If their probability of choosing that action, hopefully I wrote this out better. I did not. So you can think of it like this, right? Come over here. So the probability of ST plus 1 given your action and some other agent's action, agent 1, is also going to depend on the probability of agent 1's action given the state at T. Oh, the state of T is here, sorry. Which is actually their policy, which if they're learning is changing. Right? Okay. Yeah, the other agents are learning. This means their policy changes over the course of training. So this makes the transition dynamics non-stationary. That seems hard. It actually is hard. We lose a lot of convergence guarantees, especially in deep multi-agent reinforcement learning. So there's a bunch of work by Mazumdar that kind of says there's no shortage of work showing that gradient-based algorithms can converge to limit cycles or even diverge in game theoretic settings. So even if your game should have a particular convergence point or equilibrium, we're not sure that deep multi-agent RL can get you there. Personally, I'm not that worried about this in practice because it still tends up working and being pretty powerful, but essentially convergence to the Nash equilibria using gradient-based learning is not guaranteed due to the existence of non-Nash stationary points. So if you want to learn more about the theoretical context of this, you can look it up. But yeah, any questions or thoughts about that? Yes.
there's anything in practice it does, like for some subset of games, it does converge to a mass equilibrium, but it's just theoretically the method won't.
Yeah, I think like as with a lot of theory versus practice, like we can say that in theory we don't have a guarantee that this will work, but in practice it often ends up being very effective anyway. Yeah. It's like also like in RL, a lot of the guarantees depend on, you know, in the limit of infinite data. Well, you obviously don't have infinite data. So to what extent are you within the theoretical guarantees or not, right? Yeah. Any theorists in the crowd want to argue with me? No, not this morning. Not yet. Okay. I would also argue the non-stationarity though is kind of part of the magic about what makes RL or multi-agent RL really powerful. Other agents continually adapting to your policy can lead to better learning, robustness, and emergent complexity. Why is that? Why am I showing this picture? Yes.
So like the agent, like if like have two agents play against each other, and one gets better, the other gets better, like self-play.
Yes, that's the point you were mentioning about self-play, right? So if I'm playing a game against an opponent that's also learning, if I discover some strategy that's able to exploit my opponent, what can the opponent do? Learn to counter it, fix it, right? Now my opponent is harder. Now I have a harder learning problem, right? And as you keep adapting, you keep patching these weaknesses in the other agent's policy. So you get this like continual, you know, emerging complexity, evolving curriculum, stuff like this. That makes sense? Cool. So it's why self-play is so powerful. But we didn't answer the question of why I'm showing this picture. Why am I showing this picture? Sometimes people don't like to answer the easy questions. You had a sort of a half hand. So.
Does this move with 34? 37?
37.
I forget what the famous move number AlphaGo, right? Where it's a thing that a human would have never done, and you can only achieve that by self-playing against your superhuman self.
Yeah, you're like discovering some nook and cranny of Go strategy that even humans didn't in thousands of years, right? Like that's the idea. I actually don't even know if this is move 37. I was just trying to show AlphaGo. You know, yeah. So, but what is AlphaGo? Just let's back up a step. Who doesn't know what AlphaGo is? Oh, no one likes answering it. Okay, we got a couple people. You're very brave to say that, but probably there were more. Okay, so AlphaGo is this very famous result where DeepMind, Legacy DeepMind as it's now called, achieved an algorithm that could play Go at superhuman performance against like the world's best experts, like Lee Sedol was a champion Go player. And they like to sell it as Go has more possible states than there are atoms in the universe, which to me at the time sounded really crazy and compelling. But then I realized that actually there's a lot of things that have that many possible states. But anyway, it's a really complicated game. And they were able to achieve this from self-play. So you're training one agent with RL against an opponent that's also training with RL online. And the opponent is actually your own policy. And they do many other cool tricks, which if you read this paper for, I think it was due tonight, for Friday, then you can learn about it. So self-play is where the agent plays against itself. Essentially, you get double the experience from every game you play. So we talked about reward sparsity being a problem in RL. Why is reward sparsity a problem? What is reward sparsity? Yes.
You only get one rewards for solo trajectory.
Yeah, exactly. So I have to place all of these, you know, tiles. Do we call them tiles? Before I get a reward, right? And so that's sparse. What would happen if I only got a reward by one? And I start off kind of dumb and I'm playing a good opponent.
You get really bad credit assignments and you don't know which move is actually good. Just maybe you're stuck in a local medium because both sides of the game are bad.
That's right.
It never
That's right.
improves.
Yeah. So if you were always losing and you get a 0 if you lose, or you always get the same negative reward, you have no learning signal to figure out how I can start winning. How does self-play fix that?
At least one of your policies moves.
Yeah, one side always wins. So you, every single episode, you get one loss and one win, which you can learn from, right? So that's nice. It can exploit and correct weaknesses in its own policy. The opponent is always at the same skill level as the learner, which continues to improve. So if your opponent is exactly matched to you, then the difficulty is calibrated at the correct level. This is actually a really interesting point. So in RL, unlike in supervised learning, curriculum learning is actually really important. So curriculum learning, can anyone guess what I mean by that? Yeah.
You want to like start with like the easier tasks and then the hard.
Yeah, your task should be calibrated to the right difficulty of your policy. Why do you imagine that might be important in RL and not supervised learning? And if you're literally writing a paper about this right now, you don't. But why do we imagine that would be important? Yes.
Well, it's too hard for your agent to actually do anything. Like you're operating in a really hard environment. You want to get anything useful out of it. You're only going to get useful things out of the data.
Exactly. So unlike in supervised learning, where you're given the correct answer, so you're always getting gradients that push you towards the correct answer, RL is exploring on its own and creating its own data and learning from the reward. If you're not able to get any reward, and your reward is always 0, there's no learning signal. So it has this unique problem where you actually need to curate the difficulty so that it can start getting some traction and start learning, or curate the exploration. And so this like automatic curriculum learning is potentially a really interesting aspect of this. The other reason that self-play works well is because it's zero sum. I think I was meaning to click the bin so you could answer, but I'll give away the answer then. Zero sum games are where an increase in one player's scores leads to an equivalent decrease in the others. One player's gain is another's loss. Your reward's the opposite of mine. We're competing directly. And we'll talk about why self-play is not good for cooperative settings. By the way, if you're chronically online, did anyone see that Noam Brown? Yes, okay. Literally today, Noam Brown was talking about self-play for language models and basically saying that he only really believes in self-play in this zero-sum setting. So either the chronically online people or the people who can just like make inferences about this, do you want to talk about why he thinks that? Why do we believe in this like zero-sum setting more? What properties does it have that make it powerful relative to just cooperative training, let's say?
So in a 2-player zero-sum game, there's a theorem right by Nash, John Nash, years ago, saying that
75 years ago now, right?
oh yeah, just there always exists a minimax equilibrium.
Mhm.
So you're the 2 players.
Exactly, yeah. And so, but why is the minimax equilibrium good?
So that if you achieve that equilibrium, it means that your current policy, like the most optimal policy, would not, that you would choose a policy that would not deviate from the optimal policy. And it means that every move you makes are minimally exploitable by the opponent.
That's right. That's right. And so this is actually an important and subtle point to understand. I'm not going to go over it in as great depth in the rest of this lecture, but minimax is actually a conservative strategy. It's saying I'm trying to maximize my performance against the worst case thing my opponent can do. And so that's going to make you learn a particular policy that's really good in some settings, like competitive settings, but maybe overly conservative in other settings, actually. So even though it's true that 2-player zero-sum games have a Nash equilibrium that is this, right? That may not always be what you want. But I think there's a broader point going beyond what Noam was saying about this like competitive game. And the competitive game is the thing that gives you this property. Like this adversarial training is where you're always forcing the other agent to adapt because you can always try to exploit that, right? And so how many people have seen that like OpenAI hide and seek paper? Yeah, hand up. Oh, surprisingly few. Okay, so that is one of the papers I think we can read for this week if you're interested, but it was kind of a flashy result. They just basically train agents to play hide and seek against each other in this environment. And what they found is that if you train long enough, the agents actually discover pretty sophisticated behavior. So you could like hide behind blocks, lock the box so like the other team couldn't get in to find you and stuff. But then the seeking team actually learns to exploit like some weird glitch in the dynamics of the environment so that they can get on a box and surf on top of it, like move the box to like hop into the hiding team's area. And so the point is, this competitive dynamic led to the emergence of such a sophisticated behavior that the developers of the environment didn't even anticipate it, right? So that's like this idea that you could really emerge interesting skills without having to program them in, or even program them into the reward function. Yes.
I'm wondering about like the match.
Yeah.
Is all truth doesn't match the perfect information scenarios? Because I think isn't something like the idea behind being up with their zeros and eight? It has to do like you understand what your opponent is, like the moves your opponents can make. But if you don't have as much clarity, does the match still exist?
I think the Nash still exists. I think the idea is like 2-player zero-sum games have a Nash.
So the idea of an actual equilibrium is that you're expecting your opponent to be also optimal player. So you wouldn't expect your opponent to be like a greedy player. You would expect your opponent to also play optimal. So like both sides of the players simultaneously react to this equilibrium. It's like in the dilemma. You're expecting your opponent to follow the optimal path, the optimal strategy, because it will be dumb for them to not do so. So in Prisoner Dilemma, they fall to that. Things strategy. I'm not sure what that is.
Yeah, like mutual defection would be
Oh, yeah,
one
yeah.
way to say that. Yeah. Yeah.
Explain why debating that equilibrium leads to turbulent strategies.
Yeah, let's actually talk about that in the context of Prisoner's Dilemma. So who's familiar with Prisoner's Dilemma? Good. A lot of people. Okay. So Prisoner's Dilemma is this idea where you and I have committed a crime and the police catch us. And so this is going to be like what I can decide to do. I'm going to cooperate or defect with the police. No, with you. Or cooperate or defect for what you can do. So the idea is if we both trust each other to not rat on each other with the police, we're going to, can somebody actually look up the payoff matrix for this quickly? Because I'm going to forget the numbers. What? Wait. Oh, sorry. Cooperate, defect is 3. Is that what you're saying?
3 common.
Okay. Okay. Yep. And then 0, 5, 5, 0, 1, 1. Okay. Thank you. That's very helpful. Thank you. Okay. So this is like, if we both cooperate and we don't rat on each other to the police, we're both going to walk away with a utility of 3. Okay. So the police are going to give us a slap on the wrist, but we're not going to go to jail or something. Right. However, if you don't rat on me, but I sell you out to the police, I get off scot-free, leading to a utility of 5, right? But if we both rat on each other, we're both going to go to jail and we're going to get a utility of 1. So what is the optimal thing for you to do?
Rat on the other person.
Rat on the other person. Why is that?
Because the expected outcome is still going to be greater.
The expected
That would be
value
equal
over,
to
yeah,
the possibility of not ranking.
say again.
The
Yeah,
expected outcome is always going to be greater than or equal to the other outcome.
Mhm.
You don't take that action.
yeah. Well, and also like, if you just do the sort of, you do the rational thing and you maximize your expected value, then you're going to defect. But also the Nash of this game is one in which we both defect.
I think it's split. I think if you both defected, that's the reason. If you,
Did you read me the wrong numbers?
I think if he's cooperate with the like the police, or if he is cooperating with his friend, they don't see the wrong guy.
Doesn't really matter. It's like whatever you.
Yeah, you can change the exact values, but the point is it pays off more to in expectation if you don't know what your partner is doing to defect. Is this actually true in this case? Yeah. Because this is your expected value of if I choose defect is, I guess, 3. Oh yeah, hey, it is equal.
That's why I was like,
Wait, yeah, this should be different.
I think defect is like you're cooperating with each other. Like the D is like you're cooperating. And then C is like
Within the numbers,
Okay, guys, I'm just gonna look this up. Hold on.
It's also like how many people in jail? The higher the worse, right?
Prisoner's Dilemma Payoff Matrix. Damn it.
Wait, I think the 3 means like how many years in jail. Right?
Oh, each serves 1 year in jail. Oh, I did have this backwards. Okay, so yeah. So I think then, yeah, so it's like -1, -1, -3, 0, -2. Aha. -1, -1, 0, -3, -3, 0, -2. Okay, sorry about that. All right, so yes, the idea is I'm safer defecting. But do people actually, yes,
Consider the quality of all produce what's a good.
yeah, you're kind of preparing for the the point of the Nash equilibrium is you're preparing for the worst case scenario of what your partner might do. So you're maximizing your performance under their policy of minimizing your performance. That's what the Nash is, right? And so if they're doing the worst thing they can do, i.e. defect on you, then you better defect too. But do people actually do this? So people actually do not follow what game theory would predict in a bunch of different game theoretic scenarios. People are overly cooperative relative to the game theoretic Homo economicus rational model, right? So this to me falls into some question of like, well, I won't get into that, but yeah, people are actually more cooperative than you might think. And I think that reflects the bias that we have because a lot of what we do is integrate in society and form relationships. That's right. That's right. So if you play an iterated prisoner's dilemma, where I'm going to make a decision now, and then we're going to play again, right? Then there's actually some hope you could converge to the better equilibrium and cooperate with each other because you know that if you cooperate now, your partner will cooperate more with you in the future, and we can get this payoff over time, right? People might have this idea that we are in an iterated game. Like we have a reputation, we want to cooperate, so the people cooperate with us. Time goes on, yes.
Actually, you could, like, if you interpret this literally, and then go on to persons, then this would be iterative, right? So imagine you both did that, and then you meet.
Nice. Okay. Good. So that was a very big digression. Sorry, guys. Let's get into actually cooperative reinforcement learning, because I think that's actually pretty interesting. I'm going to end up spending more time on that now and do the competitive stuff in a future lecture. So why I think cooperation is important is a lot of what we want AI to do, if it's going to be effective at serving our needs, is actually cooperate or coordinate with us, right? If we want autonomous cars, if we want robots to be able to help me make my dinner, they need to be able to coordinate. So now we're not in a zero-sum setting. What are we in? It's a robot helping me make my dinner. How would you describe our two utilities? What is the robot trying to do? Is it trying to minimize my utility? Yeah, it's like max. We're both trying to max the game. We're cooperating. We're jointly optimizing, as we say, right? But the reason I keep showing this video, which I'm going to actually refresh this slide so it starts again, is the state of the art of robots cooperating with each other is not so hot. So these guys are crashing. This is, by the way, in a competition where you get to control all the robots, and they actually run over their own drone, which is like a thousands of dollars mistake. So yeah, it's actually a really hard problem, surprisingly, just to get agents to coordinate even with each other, let alone with us. So let's talk about how this problem works. So let's say I'm doing something like robot soccer, which is has been a popular multi-agent coordination benchmark. What would happen if I could decide the actions of all the agents at once? Do you think that would make the problem easier? You're saying yes. Why do you think so?
Well, then it gives you more understanding of where the other agents are going to go. It's like I have no uncertainty about, trying to make some sort of attack. Everyone else is moving in a way that I understand. Whereas if it's like a human or something, an agent I don't control, I have no idea what's going to happen. So I can't trust that.
That's right. So you're actually reducing, we talked earlier about multi-agent is hard because of a particular problem, which was the not knowing what the other agent's policies are going to be. So there's partial observability as well as the non-stationary dynamics. But if you're controlling all the actions at once of all the agents, those go away. It's now basically a single agent problem. So why don't we just do this? Could we do that? Why not? You just answered. So yes.
Well, there are some situations where you can't control every agent. Like if you're
Beautiful.
Waymo, you can control every car, but that you drive. That's it. Unless you win the Monopoly game here, you own every car.
I love this answer. It's so true. So you can't control every car on the road. So you've got to coordinate with agents that you don't control. Point one, very important point. But there's actually, even if you were Waymo and let's say Waymo was a total monopoly, you're Disney, I don't know, you have all the robots, or you're Amazon, you have all the robots in your Amazon factory, right? Why would you still not be able to do this? Sorry if I shut down your answer. Yes.
Computationally expensive.
It's too hard. Yes, it's computationally expensive. Yeah, okay, so this would be, you could, if you learn a policy to decide all the actions simultaneously, it is now stationary, but it's too hard because it's a combinatorial action space. So it's just like a massively hard action space, which is very hard to explore correctly. So we saw RL can kind of not work if the thing you're trying to explore over is too vast and your exploration policy is too crappy. That's basically the problem of trying to decide all the Waymo car actions at once. Yes.
Okay, Google Maps. When there's congestion on the highway, like sometimes it'll route you to some side road.
Yeah.
But if everyone gets routed to the side road, then it's just as congested as the highway. So I don't know. You're Google. I don't. How do you feel like
Oh my God. Okay. This is actually the traffic stuff is super interesting. I'm not going to remember this well enough to be able to do this off the top of my head, but if you're interested, who's learning about traffic?
Started like a couple places.
Yeah, I was like, interesting. Okay, so I'm going to post on Ed, if I remember, and if I don't, remind me. There's this Tim Roughgarden algorithmic game theory lecture notes that you can look up that talks specifically about how to decide traffic. And there's this like weird paradox in auction theory and in mechanism design. This is like a subset of game theory that says if you have, I'm not going to remember it exactly, so forgive me. Also, I can't find a view right. Here we go. Yeah. If you have like congestion in a road like this, where there's two ways to get to the goal, right? Or like traffic is coming this way and you can take one road or the other. If you actually add a way to go from here to here, it makes traffic worse. And it's kind of a bizarre result. And yeah, you can look into it. I can't go into it in the class, but it's basically like more people can opt to do this, so this becomes less crowded and stuff like this. So even like adding an extra option like worsens traffic. But yeah, I think that doesn't actually answer your original question. Why, like, how does Google Maps make those decisions? This is a whole idea of like, it's an optimization problem. So like optimizing the routes of so many vehicles at once. I think this relates to like the sequential assignment problem. I actually have some work on that. You can check out. It's like a paper linked in the doc, but I'm not going to go into it today. But it's a complicated problem. Yeah. Sorry, that was a lot of like, you can read more, but it's too much to explain today. The problem is if you try to decide the actions of all of the agents simultaneously, the sample complexity increases exponentially with the number of agents. So if you're actually trying to learn the optimal policy to route every car on the road, it's infeasible, basically. So this is known as the curse of multi-agent. We have some great theoretical work on this. So I'm pointing to some of Simon's work. You guys know Simon, he's another faculty here. So you can check that out. So the issue is, if you learn the joint policy, that's too expensive. You can't really do that. But if you want to learn decentralized policies, so that would mean controlling each agent independently. Can you see an issue with that? Back to the Google Maps example, let's say. If I'm just like choosing for each individual car whether to put on the highway or not, what could be the problem with that? Yeah?
Everything's kind of free and also do the best for themselves.
Yeah, greedy, selfish optimization might not lead you to the optimal policy. And it's just even hard to learn because the dynamics are non-stationary, right? It's what we said before, non-stationary dynamics, hidden information. So what became a frequent solution in the literature was this kind of mix of the two approaches. So centralized training with decentralized execution. So that kind of assumes during training, you're allowed to share some privileged information or some shared estimate of the value function among the agents that you're training, but then you assume at test time that that goes away and you have to be able to execute the policies in a decentralized way. So this kind of solves the issue that Jacob brought up about, you know, at test time, I have to interact with real other cars that I don't control, but it's still leveraging some level of centralized training to help learn the optimal policy. Yeah, so you can share privileged information like rewards or parameters during training, but not at test time. So this was a paper that came out in 2017, kicking off a lot of like the deep multi-agent RL stuff. It's basically just doing multi-agent DDPG, which was a popular RL algorithm at the time. And it basically says you're trying to train decentralized policies that can act independently at test times, but you're going to learn a centralized critic that estimates the value of the joint action states. And that kind of paradigm became very popular. I'll just mention a little bit more about what I mean by the critic. So if you recall, in policy gradient, you're learning a policy, but you're also learning this critic that scores it, so you can estimate the advantage function. This is saying your policy in MADDPG is going to be independent, but your critic is going to be shared. And then this becomes your update. So it's actually a pretty straightforward idea. It spawned a lot of, I put a cottage industry of methods doing this same sort of CTDE sprung up after this. Another big popular paper was called QMix. Again, we want to be able to train decentralized policies that can greedily take actions that are consistent with decentralized value estimate. And so they did all kinds of cool stuff on how do we learn this mixing network such that when you combine a bunch of selfish Q estimates into this centralized estimate, you're going to get this monotonic mixing network. So why monotonicity is important is we're saying if you're doing a shared cooperative task, you're maximizing the joint value. Then if you think you're going to get more reward, that should also increase our total global reward because we have a shared joint thing that we're optimizing. So every time, basically the total Q value should be monotonically increasing with each increase in each of the individual agents' value. So they enforced that. It was fancy. It was cool. It turns out none of this is necessary at all. So there was a big change in the multi-agent RL literature where all of this fancy stuff that people were doing turns out to just not work as effectively as, spoiler alert. Yes. So just put PPO on it and it works better. And we'll go into why in a little bit, but this is coming back to that, what I said. PPO is like state of the art in language model training. It's state of the art in robotics. It's also state of the art in multi-agent. So we'll see that in a second. But I am going to talk a little bit about my own work. Of course, I have to, in the context of coordinating in multi-agent RL. And this was it was sort of a reaction at the time to this line of work on centralized training and decentralized execution. So again, we have these issues of we want to learn this joint policy, but that's too hard. So we try to learn decentralized policies, but they're non-stationary. People were doing the CTDE thing, but again, I have the same concern that Jacob has. Like, what if I actually want to be able to coordinate with humans, right? So I want to be able to train a policy that works with other cars on the road. I'm not going to ever, during training, be able to access privileged information about the human drivers And so fundamentally, I'm creating this like out of distribution setup where at test time, I have to coordinate with agents where I've never seen privileged information about them. I just think machine learning doesn't work that well when test time doesn't look like train time, right? So how do we learn a coordinated policy, but train fully independently with only information that we can realistically assess from other agents? So trying to do this more like fully decentralized training. So the hypothesis here was that if you were able to reward mutual information between agents' actions, that would help them to discover coordinated behavior. So essentially, if you're thinking about trying to learn a coordinated policy with other agents, there's this vast exploration space. For us to be able to successfully find a coordinated policy, we both have to try the same coordinated action at the same time. And that's quite unlikely, right? So we might need a lot of data to discover that. But if we create a bias where we're trying to coordinate our actions together such that whatever you do is going to affect what I do, then we're more likely to discover that coordinated policy. All right, so the idea behind this work was to give agents an intrinsic social motivation to have a causal influence on the actions of other agents. So why this? If we're going to show that this actually relates to rewarding the mutual information, but it's also because to calculate this, I only need to observe other agents' actions. So I don't need privileged information about what's going on in their brain. I just need to observe if they turned left, right? Okay, so the way we did this was we started with modeling other agents. So we took, at the time, your standard RL agent policy, which is, processing the environment. It's got some recurrence policy. It's outputting its own policy and its own critic function from the same network. This is now so passe. You would usually learn your critic network as a different network, but whatever. And then you augment it with a supervised model that predicts how other agents are going to behave. So it says, given what I know of the state of the environment and everyone's action at time t, I'm going to predict how they're going to act at time t plus 1. So you're learning this model of other agents. Why bother doing this? What this lets you do is you can simulate a counterfactual action. So you can say, this is also conditioning on your own action. So you can basically ask yourself, if I had taken this other action at time step t, how would that have affected how other people behave? And what that lets you do, so what do I predict agent B would do if I had taken this other action instead? What that lets you do is actually assess the causal influence of your action on that other agent B. And the way you can do that is you can sample a bunch of counterfactual actions that you could have taken instead at a particular time step and put them into your predictive model to basically marginalize out the effect of your action on agent B. So over many possible things that you could have done, what is sort of the generic thing B would do, right? And then the difference between that marginal policy, so again, in terms of like KL divergence, the difference between that marginal policy of agent B and agent B's policy that actually conditions on your action is a measure of the influence of your action on agent B's policy. Make sense? Yes.
So for rewarding mutual information, how do you prevent this from happening spiraling up?
Yes. Okay. So I usually ask that question at the end of this slide. You're beat me to it by like a bullet point, but yes. So does anyone see, perhaps you, a spurious thing that could happen if I just tell you to maximally causally influence other agents?
Yeah, because then if you have one, yeah, you could, I mean, the idea would be that we're trying to reward mutual information for them to all coordinate. But if they're now all kind of not coordinating towards what we want them to coordinate to, so rather like some other goal that is undesired.
Yeah. Yeah, okay, so this is a great point. So I think what you're saying is mutual information can be high when we're coordinating, yes, but we could have high mutual information when we're competing.
Yes.
Like mutual information doesn't necessarily imply cooperation, right? So another way to put this, or the more simplistic way, is if I'm just, instead of we're trying to solve a cooperative task and I'm trying to influence you, if I only care about influencing you, I could just get in your way, right? I keep standing in your way. You're forced to walk around me. I've caused an influence on your behavior, but it's not helping you, right? So that is true. So it isn't necessarily the case that maximizing mutual information implies cooperation, but you can think of this as an exploratory bias that helps you discover a cooperative policy if that's also part of the incentive in the environment. So we're using this as like an intrinsic motivation to help explore in cooperative games. We also do two things to kind of address this concern. So we test in environments which are actually social dilemmas. So they're like spatially and temporally extended prisoners' dilemmas, where it's not clear that the selfish policy is to cooperate. So they're like the prisoner's dilemma thing. And we actually also do a variant of this, which kind of removes that problem, which I'll talk about in a bit. This is a very astute point. Yes, thank you. Any questions about that? Okay, so how do we know this is causal? We actually go back to Judea Pearl's work on causality. You can write down the directed graph of potential causal influences between your action at time step T and the other agent's action at time step B. Because you are, this is passing through an unconditioned on collider node from Pearl's notation, we know that this is a causal path and it's the only causal path, right? So this is actually the causal influence of this action on the other agent's action. But that's sort of almost like a window dressing, like you don't, whether it's causal or not, it's almost like to me a philosophical question. The key idea is we're going to give this as a reward to agent A. So agent A gets a reward if it takes an action that has more of an influence on the other agent, right? And we show that this relates to the mutual information. So the influence reward is the scale divergence term, which we talked about. The mutual information looks like this. You can transform it such that it contains essentially the same scale divergence term, but it requires summing over the probability of all the states and the probability of all the agents' actions. So that's pretty expensive, but when we think about doing RL, we take many samples from the environment. When we sample trajectories from the environment, we're sampling them according to these probability distributions. So basically, in expectation, over many sampled trajectories interacting with the environment, then we basically get a Monte Carlo estimate of this mutual information. So in expectation, over interacting with the environment, maximizing this reward will maximize mutual information between agents' actions. So you can think of this as like a form of social empowerment. So in the RL literature, there was a lot of work on this type of like intrinsic motivation. So some objective that would help agents learn in the absence of environmental reward. Empowerment was one where you try to maximize the mutual information between your actions and the next state of the environment. So you try to just like have power over the environment as like a way to learn. This is more like social empowerment. So it's saying you're maximizing mutual information between your actions and another agent. So coming back to how we test this, I mentioned we were going to test this in environments where cooperation is exactly the hard task and it's not guaranteed. So these are these two social dilemma environments. These grid worlds, believe it or not, still exist if you want to play with them for your class project, but I guess you've already written your idea in this like melting pot benchmark. The idea of harvest is it's a, it's a tragedy of the commons. So each agent, which are these little dots, wants to eat delicious apples, but if everyone eats too many apples, they become depleted, and the probability of apples growing back depends on how many apples there are nearby. So if everyone greedily just gobbles up all the apples, none grow back and they all starve. Make sense? Does anyone see why that's like a social dilemma? And maybe this is good to reinforce this like social dilemma concept. If I'm just maximizing my own utility, what do I want to do? What's my optimal policy? Eat as many apples as I can, right? But if everyone does that, what happens? Say again? Apples depleted, we're mutual defection, lower payoff than if we were able to cooperate. Same for this cleanup environment. To make the apples grow in this environment, you have to be in this river cleaning up the waste. But if I'm busy doing that, it's a partially observed environment. I can only see this view of the world. Other agents can exploit me by eating the apples that I'm basically growing. And so the way you actually establish that these are social dilemmas they do this empirically in these games. What they do is they train a policy that will always cooperate, for example, by cleaning the river, and they play it against other agents that are either cooperating or defecting, right? So they train a defecting policy that just greedily eats apples, right? And then they plot the payoff of those different defecting in red or cooperating in blue policies, depending on how many other agents are cooperating with it. So what can you see about the payoff of the defector relative to the payoff of the cooperator? Yeah, it's higher, right? So if the defecting payoff is higher and I'm a selfish agent, what am I going to do? Defect. But if everybody does that, so nobody's cooperating, what happens? Yeah, like we get lower payoff, right? So what's interesting about social dilemmas is I'm going to greedily defect. But if everyone does that, I'm over here. So I'm actually doing worse than if I've just been a cooperator. But why don't I learn to then cooperate? If I start cooperating and we're all over here, if I switch, I can get higher payoff. So it always drives us back down to the bad equilibrium. That makes sense? Questions? Okay. So weirdly, this, oh yeah. Yeah.
This would point out the same strategy or what?
Yeah, so this is what you can read off of this graph is that it is a social dilemma because if I'm choosing to cooperate, if we're tentatively have achieved some level of cooperation, individual agents are always incentivized to defect. And so that will drive us towards here. So the equilibrium point of a bunch of selfish agents playing this is actually here. Yeah. That make sense?
Yeah.
Okay. Any other questions? Yeah.
So the x-axis is the number of agents cooperate, so like, click into like further on the right, more cooperation.
Yeah, that's it. I give this talk so many times, I've never put it that way, but yes, that makes sense. So this is like more cooperation. This is more defection on this axis. Yeah. Other questions? Okay. So weirdly, just adding this influence reward is actually allowing these agents to learn to cooperate more effectively in these games. So what is going on there? And weirdly, it's actually increasing the reward above previous work on inequity aversion, which actually assumes access to other agents' rewards and does something closer to optimizing joint utility. So how is this working? Okay, I'm going to get into a bit of a digression here about partial observability. So this is a causal diagram of partial observability and state transition dynamics in a single agent case. The idea behind partial observability, this comes back to this POM-DP point, is I can't see the full state of the world ST. So I can only see an observation of ST. The observation affects my action, which affects my reward, it affects my next state, but I can't see the next state, I only see this. And so because of this, I now don't have this Markov property. From my perspective, even if I can see O1, my policy given O1 is not independent of the stuff that came before O1 because this can inform me about this hidden state, right? So yeah, you only see this egocentric observation. Yeah, so you might want to look up this POM-DP issue. So in these environments, they are partially observed. So agents don't see the full state of the environment. They see a partial view of the environment. Oh yeah, I already kind of mentioned this at the beginning of class, but I would claim every multi-agent environment is partially observed. We talked about why. Pop quiz, who remembers? Yes.
You don't know the other agents like parameters.
Yeah, you don't know their parameters, beliefs, etc. Yeah. Okay, so I did actually talk about this. Cool. Other agents' policy, memories, beliefs are hidden variables you can't observe. Okay, back to this. So why did I go into this long digression about partial observability? Well, let's check this out. So what you're seeing here is in this particular experiment, only this agent has been trained with this influence reward. And do you notice it's behaving a bit differently than the other agents? What's it doing? It does eat though. Like it just tried. See there, it ate some apples. But what's it doing when there are no apples? It stands there, it holds still. So why would it learn to do that? It does get a reward for eating apples, but it also gets a reward for this influence thing. So it learns this policy where it only moves if there's an apple nearby. And by the way, every agent's actions are like transmitted to all the other agents. So you can hear that the other agent is like turning left or moving. Yes.
Is it maybe because like it's standing still, so the other agents know that it's not doing anything, so it needs to.
Yeah, you're getting at something, right? So it's standing still and that's signaling something to the other agents. What could that be signaling? That's right.
Oh.
Exactly. So that there's no apple. So let's see. So what happens is, here's a moment where it actually had a lot of influence on this other agent. So we can, by the way, visualize, right? This is making good visualization. So what we're seeing is influence is usually flat, but sometimes it spikes. So in this moment, the influence of this agent on this one spiked. Why? Well, what happened was this yellow agent can only see what's in this red box, right? The influencer agent chooses in this moment to move towards this apple, right? We know that when there's no apples, it reliably holds still. So if it chooses to move, what does that signal to this agent? There must be an apple outside of its partially observed field of view. So it's actually sending information to this other agent in order to gain influence over its behavior. And influence is measured as, because of this agent's action, this one changed its plan. So probably it was maybe planning to go right, now it's going to plan to go up or something because it knows there's more apples up here that it can't see. So similarly, we have another example of this. This agent has been cleaning the river, right? It can't see whether apples are appearing yet as a result of its efforts. When this agent, it says turn left, but that means like spin on the spot. So it stays still. It's not moving towards the apple patch. That signals there are no apples and also influences this agent to keep cleaning. Yes.
So in this setup, it's already right.
In this experiment, yes. We have a bunch of experiments where they all try to influence each other and stuff, but in this particular experiment, only the purple one is an influencer, yes. Okay, so basically what this is all summing up to is, in order to be able to maximize this influence reward, the agent actually learned to share valuable information about the presence of apples in order to gain influence and cause the other agents to do something differently. And that helps them solve the environment because it now changes the payoff of like the cleaning agent, right? If the cleaning agent can know immediately when apples appear as a result of its cleaning, it's better able to exploit that reward and get a higher payoff for cleaning. So it helps them actually cooperate. Yes.
Isn't the version of influence control instead of like
That's right. So exactly. So I gain a reward for causing you to behave differently as a result of my action. And so we talked about how I could just like get in your way constantly and that would maximize influence. But would that allow me to maximize my apple count? So we think in these environments, if you're also trying to get your own apples, constantly, effing with the other agents is just going to be too costly, right? How do I both maximize my own reward and gain influence? In this experiment, we see that it learned to share information. But the next experiment we do actually gets at this point where both of what you're saying, which is it's not the case that I should always have to help you in order to influence you in the games we've seen so far. In this experiment, it is the case. Or feel free to argue with me if you don't think so, but that's my hypothesis. What we're doing here is we're now saying the agents have a communication policy. So they're going to learn to send symbols on a communication channel that the other agents can view. So these are just messages, right? This is a message that they can condition on. It's a cheap talk channel. Does anyone know what a cheap talk channel is? Okay, cheap talk channel means I can hear what you're saying, but I don't have to listen to you. It's just information coming in. I can condition on it and it can affect my policy or I can ignore it, right? And you can say whatever you want on the channel. There's nothing holding you to saying the truth. You can just put symbols on the channel, okay? Now what we're gonna do is we're gonna change the influence reward such that you only get a reward if your message M causes the other agent to change their behavior. So you can use your actions to just selfishly harvest apples. There's nothing affecting your actions except just maximizing your own reward. But your messages get a reward if they influence the other agent's behavior. I'm going to claim that this fixes the issue that the influence could be negative, right? I think now the only way you gain influence is you actually give valuable information to the listener. Why do I think that? So again, cheap talk. Listener, free to ignore what you're saying. What is the listener trying to do? This comes back to this point about why social learning tends to be good. The listener is doing what? It's an RL agent. It's trying to maximize rewards, right? So it's kind of doing its best to exploit the environment. It's doing a state-of-the-art strategy to get its own rewards. It's just optimizing for rewards. What's the only reason it's going to attend to the message you're putting on the channel? If it helps it get more rewards, right? It's learning the optimal policy to maximize rewards, condition on all this stuff. So the only way it's going to change what it's doing is if the message is actually reliably helping it maximize its own rewards. So I'm claiming that influential communication in this setting should benefit the listener. All right. This is at the time, but this was like pre-LLMs, right? People were very interested in this emergent communication setting. How do you learn a communication protocol from scratch, from nothing? It was kind of interesting, except that nobody ever talked to an actual linguist. So I think it kind of died. Like if you wanted to study this question, I feel like this is a linguistics question. Why are like a bunch of these multi-agent RL people studying it? But in any case, there were some theoretical results that says cheap talk between self-interested agents won't happen. Like we shouldn't share information. And empirically, we saw a bunch of communication work in multi-agent RL showing that they didn't learn emergent protocols. Yes.
Oh, I think cheap just so just to confirm my own, cheap talk just means that communication just doesn't help with your payoff, right?
Sorry, it means that communication channel is like ungrounded. So you don't have to listen to it and I can say whatever I want. So there's nothing ensuring that whatever messages are placed on the channel relate to anything in the environment.
But like, how do you make sure it's cheap talk not? How do you make sure like I can say whatever I say is not an information? It's not informative.
Right. Well, so what we're going to measure is, do they actually learn to say anything informative that does relate to the environment? So that may happen, but we're saying like the structure of the channel doesn't enforce that. Does that make sense? Okay. So this was kind of the background for this work. And then what we saw is that not only when you add this influential communication channel, that increase their ability to cooperate in this environment, but that we actually did an analysis of, are they talking about anything? So we looked at not only the mutual information between the messages and agents' actions, but we also looked at the mutual information between the messages and things in the environment. So like, do they tend to use the same message when the same stuff in the environment is happening? And we see that, yes, they actually learn more meaningful communication protocols in this setting. But this is kind of the coolest slide. So remember I was claiming that if you manage to influence someone with cheap talk, you should have given them some useful information that benefits the listener. And what we see is that if you plot the individual rewards, and visualize everything, the individual rewards of agents and then how much they are influenced. So like to the degree to which they actually update their actions based on communication messages, we see that those agents that are more easily influenced tend to get higher individual rewards. And this is actually very consistent across hundreds of different hyperparameter settings, both environments, like strong, significant correlations between being influenced and getting higher individual rewards. So we think this supports that hypothesis that they're actually gaining some beneficial information from listening on that channel. And in these experiments, all agents are trained to influence each other and maximize rewards. So it's like all this like N-way communication. All right, so in conclusion, whether this action influence leads to cooperation does depend on the environment. You can have high mutual information in a competitive setting as well. We think in this case, for self-interested agents, communication was one of the cheapest ways to influence other agents without costing too much of your own reward. Influence on self-interested agents via cheap talk communication must benefit the listener. But that only is true for agents interacting repeatedly. Why do I say that? Yes.
Like you can always, for one, that's so
Yeah, so if and we see this on social media, right? No, if we come in with a communication protocol that we both understand and I'm never going to see you again, I could say whatever I want. That might cause you to update your behavior, and I would never suffer a penalty from that because we're not interacting again. But if these agents are interacting repeatedly, if I tell you some bullshit, what are you eventually going to learn to do? Not listen. So then I lose influence over time. So this is a characteristic of the repeated game, right? Okay, so in conclusion, social influence is a unified method for promoting both coordination and communication in multi-agent settings. You can learn socially but train independently, which at the time was so cool. So it's fully decentralized, does not require access to shared parameters or rewards. There was some follow-ups of this work showing that it was like a pretty state-of-the-art method for a while, including in like robot soccer, Google Research Football. But coming to the spoiler alert. Oh wait, do you have a question? Yeah.
I was gonna say, isn't it somewhat like, you know, when you play poker and stuff, where like it should be like sometimes you should send things that are like, you know, accurate communication, but then also sometimes you should send total bullshit that can exploit bullshit that sense, and then you should have like a problem that you make sure it's actually happens. Like, should you also explain that, or is that like just not all?
You just gave me a good idea, but actually I think in poker you want to minimize the influence of your tell on the other player, right? Like if you had a tell where you like twitched every time you had a good hand, then you would actually, that tell would have like a lot of influence on the other player's betting, but you would have to like throw it out as like a fake signal sometimes to like reduce that signal. I guess it's like reducing the mutual information between your tell and like the other player's action, you know, the optimal action for the other player. Yeah. Interesting question. More questions before I move on? Okay, I'm going to get into this and then we'll have like a discussion at the end. So I kind of give a spoiler alert, but the new state of the art from Marl is this independent PPO. So there's a couple of papers on this. I personally recommend this one because I think it does a better job doing careful analyses as to understand why PPO is the state of the art method. But it is. And so let me see what I have on the next slide. It just crushes QMix, right? So QMix would have been the previous state of the art. This is PPO in red. So if the environment is simpler enough, it's fine. But it's just the only thing that's able to learn in some more complex multi-agent environments. And this is my own work. So this, I think, red line is this like influence-based stuff. Independent PPO also crushes the influence-based stuff for soccer. But so why is independent PPO? So this, what I literally mean is each agent is just PPO. That's it. There's nothing special. There's no multi-agent anything. You're just, everybody's running PPO. Why is that better? Yes. Oh yeah, you can play with this for your project if you want. It's in our doc of environments. This is the Google Research Football environment. So you're like controlling these little players, you're trying to play football, football meaning soccer. Yeah. There's a team in Zurich doing this. Okay, why is this so much better than everything that came before? How does PPO work again? What's the key idea behind PPO coming out of like TRPO? If you remember, we did this in the very first lecture. What does it constrain? Mikhail, you looked at me, now you're called upon.
Okay. TRPO is uses counterfeit gradient to update. So PPO simplify that, making it compatible with this has a gradient descent. And PPO actually have three forms. The first one is one actually make it a constraint optimization problems and then improve it. So it's set to board and move the tail to become auto equalizers. Then the third one is the clipping, which replaces the tail regularization to become just flip the objects.
Very nice. But KL between what and what?
Tail between
What's the,
the
yeah.
curve, the policy that generates the experience versus the curve.
Yes. It's basically like your current policy and the previous iteration of your own policy weights, right? So you're constraining how much you're updating your own policy. Why would, if everyone in a multi-agent setting is constraining their updates, and remember the motivation for PPO was that it's not constraining the weight updates, it's constraining the policy updates. So if you recall, in TRPO, it was like DKL between your policy high old, right? And your policy that you're doing now, right? So it's not the weights that are being constrained, but it's literally your distribution over your next action. So it's a constraint in policy space. If I'm constraining this divergence, what am I doing to my policy learning?
Slowing it down.
Slowing it down, correct? I'm making more smooth updates to my policy. Why is that good for multi-agent? Coming back to the very first thing we said in the lecture. Stationary, yes. So the non-stationarity of multi-agent, meaning everyone's policy is changing and is changing by transition dynamics, is part of a big part of what makes it hard. So when everyone is slowing down that non-stationarity and updating in a more stable and smooth way, that actually makes multi-agent works a lot better. Yeah. So PPO minimizes changes in policy space. If other agents are using PPO, their policies change more slowly, reducing non-stationarity. And so again, this paper has like a nice analysis of that. This is independent learning all you need. So I encourage you to check that out. I already said that. Thanks, past self. Okay, so we're out of time for today, but we're gonna talk in a future lecture about whether learning decentralized policies is actually enough to coordinate with humans. The answer is actually no. So if you're dissatisfied that just put PPO on it is the best answer to everything, it's not. You have to do something more complicated. Okay, back to questions. Yeah.
This, I mean, your application domain and your initial policy for that actually like not good enough. Like, it's not very good. And you're starting from it. PPO wasn't really work well.
Yeah, I mean, like PPO is going to take longer. I'll just go to the soccer example. It's going to take longer to find the coordinated policy if you're learning from scratch and the environment is harder. But if you can run for enough time steps, maybe you can always find it, like kind of monkeys on a typewriter rule. So then basically the kind of state-of-the-art trends in this area is like, yeah, PPO plus JAX. So if you can run everything in JAX with like super, super fast, collect so many samples, then that just works. I don't know if that answers your question. Yeah.
These types of setups, especially with the PPO, so like every agent is be updating their ways for it. share the same policy?
Both are true. So both kind of work. This result I'm showing is everyone is running their own set of weights, but actually the original paper, I believe this one, and maybe also this one, it's like one set of weights is controlling each agent in the soccer team. Does that make sense? But it's like the experience from all the different agents updates that set of weights, and it's just PPO. So both kind of work. It would depend on what you need for your application. I would say, so reason I did it this way, this figure is actually just, I plotted my own thing on top of a figure from a different paper. This was from like celebrating diversity in multi-agent systems. That paper is talking about how learning policies that are quite different from each other, like they deliberately maximize KL between the different agents, is better for soccer because you can learn like specialized roles. So like one is a defender, one is a forward, or whatever, right? So you might, if you want that kind of like specialization, you might want each agent to have different weights.
I guess it's a follow-up, but
Mhm.
the social dilemmas. And
Yeah.
if all the agents isn't it pretty easy for one agent to just like exploit, like become a effective?
Yeah. Exactly. Yeah. And so that's what makes it hard. That's the social dilemma idea. More questions? Yeah, and so I didn't get a chance to talk about the satellite assignment stuff, which you can check out. It's like linked from the thing. And also we've done some work in studying climate change as a social dilemma. So that's actually Carrie's work as well. And so you can use multi-agent techniques to kind of study what is the defecting behavior in like a multi-agent simulation of climate change. I think it's really interesting. And Kai's work too. Yeah.
How do we use more like how we construct stuff? Like I know it can be over,
Just works better.
but isn't that like skill issue?
Yeah.
You had a valuable thing that worked.
It's absolutely a skill issue. And this is a really important point, right? We talked about in the beginning of the class, what if you're like RL post-training pipeline, if you're OpenAI, PPO works significantly better than DPO, but some people are still using DPO. It absolutely depends on the quality of your implementation of these things and whatever weird arcane magic hyperparameters you manage to find for your setup that gets it to work. So right now we're in this potentially local minima of everything is PPO because that's what's working. But yeah, maybe that is a local minimum. Maybe there's something that works even better. Maybe we'll see a resurgence of Q learning because of some trick that gets it to work. If you want to look for a trick that could get it to work, I would look at Aviral Kumar's implicit under parameterization stuff. I think that's actually really insightful and interesting about like why deep RL is actually hard to optimize. So that stuff's cool. But yeah, maybe you'll invent the next PPO. That'd be cool. All right, that's it for today, but looking forward to seeing you write up the next set of papers.